Hi, let's just keep going. For today, I wanted to include actually a comic. You may have heard this joke before. Two guys walk into a bar. First guy says, I'll have H2O. Second guy says, H2O2. Second guy dies. And I don't know if everyone fully understands the joke behind it, but I specifically like this one because there's usually two more panels on the bottom where this person here, we'll call them person one, jokingly says, wow, stupid choice, or something like that, or idiot. And I'm always confused, because I'm not 100% sure if person one is referring to person two or person three, who was the actual person who took the drink order. But regardless, we've got two different chemicals that we're talking about, right? If we say it verbally, H2O versus H2O also, but then the joke is that there is this compound H2O2, hydrogen peroxide. With this Lewis dot structure, it's got different properties, of course, compared to water. But really, relating it back to what we're talking about, there's some really large differences between water and this hydrogen peroxide in terms of their ratio of elements, their percent composition by mass. And so we can start to relate that idea of like, how do we figure out some things about like, we can do some. And so I thought this would actually kind of connect to what we've been talking about, because we've talked about this process on the left where when given a chemical formula, you can relate that down to a number of particles. You can relate the number of particles to a like mole ratio. If there's one Na and one Cl, that's like saying a mole of sodium and a mole of chlorine. And then furthermore, we've learned how to do that mole to mass conversion. Remember, if you have a mole of Na, we can multiply by 1 mole of Na, 23 grams of Na, and that dimensional analysis is still there, and we get our 23 grams of Na. And we can set up a mass ratio, which then we can turn into a percent composition by mass. Then, knowing all of that, is it hypothetically possible to work the entire process in reverse? Start with a percent composition, go through a number of steps, and land at a chemical formula? And the short answer is yes, but maybe not to the degree that you're hoping. So here's some example data. Two bottles are found in a lab, and they're both labeled as having a pure compound of hydrogen and oxygen, and here are your two percentages. Now, knowing what we know, that there are two compounds that exist, it might be easy enough to say, yes, one of them is H2O, and one of them is H2O2, and all we have to do is figure out the percent composition in H2O and H2O2, and we're done. That's all well and good, but maybe try and think a little bit larger to say, what if you got information that says something that you don't know about a chemical that you don't know about? It's nice to figure out a process when we know where the answer is going to make sure that we're doing the process correctly. So we've got our two components, 11.1% hydrogen and 88.9% oxygen, and the other one. But these percentages on their own, right, if our relationship back to a chemical formula, like we saw on the previous slide, is moles, our connective tissue here is moles between the chemical formula and the percent composition, I know that one of the steps to get to moles, mass is something we've been working with. So how can you get from a percent composition by mass to an actual mass itself? Well, how much compound do you have? If there were 5 grams of the compound, 11.1% of it would be hydrogen for, compound A, and 5.88%, you multiply, right? 0.0588 times 5. So I guess if we wanted to turn this into an actual mass, we just have to pick a mass, because it doesn't matter whether you have 5 grams or 50 grams or 500 grams, the percentage is always going to be the same because it's part over whole. There'll be more of the part and more of the whole. It's proportional. So let's pick an easy number. For sake of argument, just say that there's 100 grams of your compound. Why? Because 11.1% of 100 is 11.1 grams. And 88.9% of 100 is 88.9 grams. And so you can actually very quickly just remove your percentage sign by assuming a 100 gram sample, and then you get, the numbers you need. Okay, great. Now that we have that number, we can relate that number back to our moles like we said before. In just the same way that we did with our previous video, we're going to convert from grams to moles. So we write our given quantity. We're going to multiply by grams on the bottom because we want them to cancel, and moles on the top. I believe actually it'll be 1 mole of H, I believe it's like 1.007. So for the sake of argument, we're just going to call it 1.0. We're going to round it. And then our units of grams will cancel, and we'll have 11.1 moles of hydrogen in this 100-gram sample. Then we do the same thing for the oxygen for this sample. In this case, we're going to write 16 on the bottom because 15.9994. And we get 5.56 moles of oxygen. And then for a next step, we're going to do all of that again for the second compound. I'm going to write it down here on the bottom, condensed. And just to make sure that that you can see the whole process if this is something you're still stumbling with, make sure to cancel out all my appropriate units for all 4 of these conversions. Great. We now have a mole ratio of hydrogen to oxygen for each of these 2 compounds. But that's not a direct chemical formula. If we see, there were still a couple steps to get from the chemical formula to mole ratios. And, just this here, between these 2 bullets didn't really look like much happened. So can we just get away with that? Can we just write H 11.10 5.56? I mean, that was the mole ratio. I just don't really think I've ever seen decimals in a chemical formula. We can't do that. But what is nice is that if these numbers are based on moles and therefore a number of particles, in every chemical formula there has to be a whole number of atoms. So this number, this set of numbers represents a whole number ratio. We just have to figure out how to get there. And the easiest way to start setting up your whole number ratio is a process called normalization. And normalization is just a big word that means make one of your numbers 1. And the easiest, what I would suggest here is we're going to make our smallest number 1. We need to divide by 5.56. However, since this is a mole ratio in a compound, whatever happens to the oxygen is going to happen to the hydrogen too. We need to maintain that ratio. So when we divide both of these out, we get, obviously the O here is a 1, but we get 1.996. I mean, that's close enough. I think that's close enough, if we can all agree. That should be a 2, which means that this first compound, compound A here, is actually water, the 11.1% hydrogen. That ratio of masses corresponds to that ratio of atoms. For the second one down here, we can do the same process, but you can kind of see if they're both the same, we're going to divide both of them by the same number. It just worked out that nicely. And we get H1O1, if you will. That doesn't, I don't like that. Hydrogen has 1 valence electron, oxygen has 6. So that, what we wrote here, this can't exist. Chemically, that's an invalid compound. It's not stable. There's no octet thing going on if that's still the rule you subscribe to. That I'm not really calling a rule because it's not really an octet. But still, that isn't really anything other than a ratio of atoms. In both cases, this is a ratio of atoms. In the case of water, obviously, it also works. But collectively, when we go through this process, what we're going to arrive at is something called an empirical formula, which is just your simplest whole number ratio of atoms in your formula. In some chemical formulas, the actual chemical formula is the same as the empirical formula, like water. But in some cases, like this HO compound, it's not. So on the bottom you have your glucose, and I've shown you that the empirical formula for glucose, not the same. So that's where that joke comes in, where it's like, I'll have H2O2. You can relate this percentage back to that chemical compound through this long math process. There's just one more thing I want to mention. Sometimes you go through this process and you don't really get to a place where you're done. And I'll show you what I mean. Our first step is to assume a 100-gram sample. So our masses are the same number just with grams at the end. Our second step is we needed to convert to moles. And in both cases, it's 1 mole, and I think it's 14.007, so we'll say 14.0, and then again, 16.0, 15.9994. The periodic table is good like that. A lot of these numbers are close to a whole number. So we end up with 2.63 moles of N and 3.95 moles. Now, again, I know what you're maybe thinking. When you took a look at the previous slide, when we had our number of moles after normalizing, I said this was close enough to 2 to call it 2. And you might be saying, yeah, the same thing. This 3.95 is close enough to 4 to call it 4. But then this isn't. This 2.63, not remotely close enough to 2 or 3 to round. So we do want to make sure we're always keeping in mind that our normalization step should be this last step to get all of your numbers into that ratio. So our normalization step actually hasn't taken place yet, so let's do that. We're going to divide both of them by the smaller of the two. You could divide by the larger of the two, but then obviously one of them will be less than 1, so you'll still have a decimal. The nice thing about this is usually by dividing by the smaller of the two, we're going to end up with a simple whole number ratio. 1 to 2, 1 to 3, 1 to 4. Is a 1 to 1.50 ratio. So that's not our empirical formula. It's not a compound. It's still not there yet. But we know that the ratio is 1 to 1.5. And there's an easy way to solve that, kind of like what we saw in our balancing chemical equations. Whenever you get a 0.5, one of the things you can do is to multiply to get rid of your decimal. 0.33 would be like 1/3, 0.25 would be like 1/4, and 0.5 would be like 1/2. So if you multiply both of these by 2, you get N2O3 as your empirical formula. So sometimes there's this one added step after normalization where you have to multiply back after you divide to make sure that you have a good-looking whole number ratio. So to sum things up, it is possible to get from a percent composition back to a chemical formula, but that chemical formula is empirical instead of this molecular formula, which we'll be talking about next. Your steps to really pare it down is percent to mass, mass to mole, divide by the smallest, and then maybe multiply till whole. And even after doing that, if you get into a position where you're within 0.1 of a number, like if you're between 1.9 and 2.1, you can round that back down to that whole number and then be done with it. Thanks for watching.